Hello. In this video presentation, I'm going to walk you through some example problem solutions. There's a presentation. This PowerPoint presentation is in the content, and this is the video presentation of that content. So the first one I want to talk about is example 1.3 in your textbook. This is a cable structure, and then I set this up as if it was the preferred format. So you're given a cable system with geometry as shown. Find the angle B between cable AB and cable AC. So we're looking for this angle right here. And I kind of like this problem. It goes through several steps. Now, first of all, we need to recognize that triangle ACD is a right triangle. And then using that information, what we can do by calculating the hypotenuse, we can get the length of side B. And running through this equation right here, we calculate the side B as being 12.65 feet. Now, once we have 12.65 feet, we now have this oblique triangle, and we know all three sides, A, B, and C. What we're trying to find out is what this angle here is. So therefore, we're going to use the law of cosines. B squared equals A squared plus C squared minus 2AC cosine B. We're going to solve that for cosine B. We're going to take the inverse cosine and then find out that our angle is indeed 128.7 degrees. So this was an example of how we need to be able to solve triangles for statics problems. Now here's some problems in Chapter 2. Chapter 2 is rather simple. We're talking about rectangular components of a force. So this problem states, this is example 2.3, given the 400-pound force vector shown, find the rectangular components, that's horizontal and vertical, rectangular components of the force. And here's the solution. We're just going to use our trigonometric functions. The px is the is the horizontal component, and we solve for 306 pounds. Now it's pointing in the negative direction. Okay, if we notice here on our axis, this is the x positive direction, this is the x negative direction, therefore px is acting in the negative direction. And then we solve for py, and it's acting in the positive direction. So next one was example 2.3. Example 2.5. This is another type of problem where you need to solve for components. You've probably seen this in physics. You've probably seen this in statics. It's the infamous block on an inclined plane, in which case the two directions are parallel to the inclined plane and then perpendicular to the inclined plane. We use this a lot in physics. I'm not going to talk about that one too much. It's rather simplistic. You can review that on your own. This one here is another example of rectangular components of a force. But in this case, we're not giving you an angle here. We're giving you a slope. The slope is a little bit different to use for solving. So I'll work through this one. So given a force P is acting at a slope as shown, find what you have to do is resolve the force into its rectangular components, vertical and horizontal. And here's the solution. So what you can do is calculate the hypotenuse of the slope triangle. That's 2 squared plus 1 squared, the square root, so you get the square root of 5. That's the hypotenuse. And then once we have that slope triangle, what we have is we can draw our force triangle too, where px and py are the force components that we're trying to find. So the slope triangle is similar to the force triangle, therefore the sides are proportional to each other. And then finally, using those proportions, we set up this proportional equation right here, and then using that to solve for what px and py is. So in this particular case, we're not using the angle and the trigonometric functions. We're using proportionality, because we were given the slope, a 2-to-1 slope, instead of an angle. You'll see that a lot in this textbook. It'll come up again. Okay, so in chapter 3 was about resultants of coplanar force systems. Example 3.2. Again, you can follow along in your textbook on these. But in this case, we're given this concurrent force system shown. When I say concurrent, I mean that these two forces are acting in the same point. So you're supposed to find the resultant R, and that's the magnitude, sense, and direction. In this particular case, one of these forces is defined by an angle. The direction is defined by an angle. And in this particular force, the direction is defined by a slope. So in which case, what we're going to do in this part of the solution is we're going to calculate what the resultant is of the x components. And essentially what we do is the resultant in the x direction equals the sum of the x components of the two forces. And that's what's happening here. So once we do that, we know that the positive sign of this force component means that the force acts to the right. Then we're going to do the same thing here with the y components. Okay, so now that we have the y and x components of the forces, we can solve this for the resultant by taking the hypotenuse of those two and then finding the direction by taking the inverse tangent of ry over rx. Now the other thing that's really interesting about these components forces is that it doesn't have to be a two-force concurrent system. In this case, we have four forces, and we do it the same way. We calculate the x components and the y components of each of the forces, and then we add them together. And the best way to do that, like we're showing here in example 3.3 in your textbook, is we calculate what the x components are for each one of the forces and what the y components are for each one of the forces. We sum those together, and then we can calculate the resultant based on the hypotenuse of the x and y, resultants of the x and y components. Okay, chapter 4 talks about equilibrium. These problems are just a little bit different. I mean, they're the same thing in that you're using force triangles to solve for things, but we're using the concept of equilibrium here. So therefore, if we're doing things by components, the sum of forces in the horizontal direction equals 0, and then the sum of the forces in the vertical direction equals 0. Thereby the definition of equilibrium. I included this slide just for your reference. Okay, example problem 4.4. What we're looking at here is a weight that's supported by a flexible cable attached to a boom. So given the weight is supported by a tied boom as shown, what we're supposed to do is find the magnitude of the force in the boom and the tension force in the cable. Here's the solution. First of all, what we're going to do is recognize that the boom and cable are two force members. Therefore, the line of action is known. Then we're going to sketch the free body diagram of point Q, and that's what this upper graph is. And then based on that, we're going to draw the force triangle. Now remember, it's an equilibrium problem, so therefore this force, all the sum of the forces all equals 0. So we got this nice force triangle. So what we have here, we have the three directions, we have the three angles, the 40 degrees, the 80 degrees, and the 60 degrees, and we know what one side is. So therefore, since we know all three angles, we can use the law of sines to calculate the forces T and C. Okay, so here we set up the law of sines, and here we calculate the T and C. So alternately, this same problem may be solved by the methods of components. And we do that by summing forces in the horizontal direction and setting them equal to 0, and then summing the forces in the vertical direction and setting those equal to 0. And I'm not going to go through that here, but see your textbook on page 69 for this solution method. Now keep in mind, you're going to have 2 equations and 2 unknowns. So you're going to have to solve this by substitution. So our last problem is very similar. We have a block that's supported by 2 cables as shown. The magnitude of the forces in the cables is what we're supposed to find. So solution. We are going to recognize that the cables are 2 force members. The line of action is known, and the cables can only be in tension. The first step is to calculate what the force. This is a system international units. The mass of the block was given in kilograms, so therefore we have to calculate what the force is in newtons. And then we're going to draw this free body diagram. Again, similar to the last one, we're going to draw the force triangle. We're going to solve using the law of sines. And then we could also do this by components, but this is the most straightforward way to do this problem.